Chris, and let's start with the second 45 minutes. So we have seen in the first hour the measurement-based quantum computation paradigm in continuous variable, and we have just said that we have our state, and then you have all your state 0p, 0p, and so on, and then you measure certain quadratures or certain observable and so on. And you teleport, choosing how you measure, you teleport a different transformed state. Then we said that this commute, so I could also interpret this like a cluster state. I have my cluster state before. In this case, if I go on writing like this, it's a linear cluster. Then I attach my input state to the cluster, and then we perform measurements indicated by the arrows. And then you get here some desired transformed state with the byproducts, but you get here psi out. But the problem is that in real life, no way in the lab, ask Chris, no way in the lab you can generate infinitely squeezed states. So then these are going to be finitely squeezed states. Instead of being eigenstate of P, they have a certain squeezing, which means that when you do this, you are going to add the noise.
Do you know what the most squeeze you can get is?
Yes, for a long time the record was by Schnabel, and it was 14 dB.
14.
Where dB, every time I forget, that is 10 log 10 of a ratio. And the ratio is taken with the vacuum fluctuations. Or sometimes they take it.
One compared to the other.
Yeah, one.
But it's the same, or?
No, because the vacuum is this.
Ah, but what you said was 14 dB compared to that.
14 dB. I think compared to vacuum. Yeah. Or maybe it was, yeah, that order of magnitude. So the problem is this is not going to work. We are going to have a big Gaussian noise that is going to spread our output state, and we cannot really do fault-tolerant computation with that. So then the problem was solved by Gottesman, Kitaev, and Preskin. In 2001, they introduced a state that is called the GKP state, that then Minikuchi in 2014 used to do MBQC in continuous variable fault tolerantly. So the idea is that we are going to do this now. If we manage all the calculation, if we don't manage what we can do, the idea is that here you get a lot of noise. So the idea is that here you do some extra. So this is your state. You entangle it with the GKP that I'm going to define. Here you entangle it with the GKP. And so you need some extra squeeze mode. And then here you get your psi out that is now corrected in some sense. So you can tame the Gaussian noise that comes from the finitely squeezed state, provided you have these kind of states that are very crazy, but have been implemented experimentally in 2018 and 2019 into groups. One the Yale group, and the other the Jonathan Holm group with trapped ions in Switzerland. So they are not anymore science fiction. They have been science fiction for 17 years, and then they have been realized experimentally. So what are these? Let's first talk about ideal GKP states. So, meaning again infinite squeezing. So first I define them, and then I will tell you what the concept is. So these are spikes of delta peaks. It doesn't matter, the second wave function. So the idea is the following. We come back to digital, like qubit type quantum information. It's a little bit analogous to the classical computation, where they were using analog computers but then when it came about error correction, they thought that error correcting bits is easier. And then with continuous variable is the same. We still want to use the continuous variable hardware. So the physics is still a continuous variable, is still the harmonic oscillator. But what we are going to do is that we are going to use this hardware to encode qubit type quantum information. So if you take a wave function then of the oscillator, the vacuum will be this. Then what did we introduce? We introduced Q, so infinitely Q squeeze states will be a spike here. And these GKP states, they are as trains of spike that are placed for 0 at all even multiple of square root of pi. So then I take 2 square root of pi, 4 square root of pi, and then minus 2 square root of pi, minus 4 square root of pi. And then I have these infinite peaks that correspond to my 0 logical state. And then the 1 logical state is also a train of delta peaks, but they are placed at even multiples, at all the multiples of square root of pi. So then they are going to be placed here. Where this is square root of pi, 3 square root of pi, and so on. And this is the 1 logical. Chris, questions?
What is this representation on the y-axis here? Because can you have negative
Yeah, you can.
as well?
Yeah.
Okay.
Yeah, if you want, I can write it. I didn't write it, but I can. So, so this is equal. So this is the wave function in Q. You write the wave function in P. For the 0 logical, you get all of them. And for the 1 logical, which in the Q is given by the odd. In the P, you get exactly as you were saying, even phases. Mm-hmm. Then the finite squeezing version correspond to having a Gaussian peak and a Gaussian envelope. But the idea remains the same. So there is a Gaussian envelope here and a Gaussian envelope here. I'm not going to write them, but it's quite clear. They will be written like the sum of, instead of delta peaks, we have Gaussians, and then we have to take a certain Gaussian envelope. In the ideal case, as you see, they are eigenstates of the translation operation when you translate by a multiple of square root of 2 pi. And indeed, this is how they have been prepared by the Yale group. They managed, by coupling with a transmon, to measure somehow the displacement operator. So they were fabricating states that were eigenstate of the displacement operator. And now, so we are set to define the second notion of CV universality. In the presence of an encoding, basically, let's say that we fix on GKP. So you are able to implement all the possible quantum computations if you are able to implement all the possible qubit computations. So here you want to show that you are able to implement a universal gate set for qubits encoded in GKP states. What are these operations? So what do they correspond to? Some are very, very easy to understand. For instance, let me do the simplest example. Then I'm going to write later the universal gate set, but the X logical operator is what we call the X of S before, but with S equal to square root of pi. So this you can understand very easily because this is a displacement in Q by square root of pi. So here what does it do? It does that if you displace from the white spike, you hit the pink spikes. Basically, if you act, what I'm saying is that if you, I'm saying like this, and this, so it has the same action as the qubit Pauli X operator, but here is encoded in GKP, and it works that it is this particular continuous variable operation, because if you apply displacement by square root of pi to this encoded state, you get, from the 0, 1, you get the 1. Is it clear? Yeah.
Why is like square root of pi chosen and not pi, for example?
Okay, there is this, so the square root of pi allows you to define states that have symmetric properties in Q and P, in the sense that they have symmetric noise properties, for instance. If you would choose any other possible choice is feasible, but then they would have a different structure in Q and P, and then they would allow you to correct, for instance, for some larger error in Q and smaller error in P. That would be possible. It depends on your error model. If noises in Q and P are more or less likely, then it's better to take the square root of pi. And why mathematically, you find it in the GKB paper, which is a very nice 30-page paper that contains so much information. It's so dense, very good paper, yeah.
It is somehow related to the commutator, if it's like...
Oh, yeah. I think it comes out of when you, like, it's just so that everything is unitless.
The square root of pi?
Yeah, I think so.
No. Here, the square root of pi, you have it no matter which conversion. Then, depending on the conversion, you can get a square root of 2, or a 2, or nothing in front of the square root of pi, I think. Probably. I'm not entirely sure either.
But you could just change all your displacements to 1 over square root of pi. Like, it's just a scaling factor, right? Oh no, because, yeah.
Then in the other quadrature, you get the pi. Yeah. No, this is the one that you get for symmetric noise properties, if you want to be able to correct for symmetric.
I thought this allows us to measure that position and work that at the same time.
The position and momentum at the same time.
And by that factor, so that with this factor, those operations are commute with each other. If we add that factor.
They don't commute because it's like the Pauli, it's like X and Z. They don't commute X and Z. They give a commutator, and here you will get the same if you do it with the, you really get the same commutator type relation like with the Pauli, standard Pauli one. Okay, but let me move a little bit forward. Okay, so in totally analogous manner, by the way, I'm using different notations. Let's maybe stick with logical. So I remove the bar, which also means logical. The Z logical is, as you can guess, square root of pi in Q, which was Z that we defined the previous hour of square root of pi. And it has the same action as a Pauli Z operator on the GKP encoded qubits. Sorry, there is no plus. Oh, sorry, so then probably this had a minus. Okay, what about the other operators? So the CZ gate encoded, it's very nice. because it remains equal to the standard Caesar gate. And then the Fourier, the encoded Hadamard is the Fourier transform. And this probably you can also see, I suppose, that if you take, so what you would like to see is that H on 0L, it should give you 0 plus 1, logical, over the square root of 2. So then if you take the 0L is this one, the 1 is this one, so you have the peaks in, so if you sum the two, you should get the peaks everywhere, every square root of pi. And basically, if you take the Fourier transform of 0, you get now this wave function in Q, which is the sum of all the possible peaks at all the square root of pi, not only other. So it works, really they work. And so the point with GKP is that all these Clifford qubit operations, they map to Gaussian continuous variable operations. But so far in our set, we are having the Z logical, we are having the CZ logical, we are having the Hadamard logical, and we still miss, what we miss, will you remember from the Anton course?
TD.
Yes. So this operation is a non-Clifford, and it maps in GKP encoding in non-Gaussian operations. And in particular, the T logical is given by pi over 4 2q square root of pi cube plus q over square root of pi square minus 2q over square root of pi cube. So this is non-Clifford and non-Gaussian. Okay, so now we are going in the remaining time, as much as the time will allow, to understand how the GKP states allow for quantum error correction and enable fault tolerance. What we are going to study in particular, also another thing that I would like to mention is that they are designed to correct for arbitrary noise in displacements. Tell me, Chris.
I'm just blind.
Oh, okay.
Minus. What is that last term?
No, not cube.
Yeah.
Linear.
Mm.
Nothing at the exponent.
Otherwise.
Yeah, otherwise it's very much non cubic. So this code is designed to correct for arbitrary displacement, and this is what we are going as much as possible to show. Then the idea is that since any map, so this is a little bit non-rigorous what I'm going to say, there is some subtlety, but since each map can be decomposed in displacements, then GKP states allow to correct for any kind of noise. The truth is that each map will be a certain noise distribution, and then U1 UQ VP rho UQ VP, where in practice this can be different, UV and U1 V1. So then this is not exactly a displacement. It will be a displacement if they will be the same variable, then it will be a displacement of your map. But this is a true decomposition of any possible map. Still, GKP state, if you take something like this, like your noisy qubit, by the error correcting gadget that we are going to write now, down now, basically they project onto a specific instance of displacement. It's like you have a correction where you have a certain rotation noise, but when you do the measurement syndrome, you project onto an error. And here is the same. When you do the measurement syndrome with the gadget that we are going to draw, you project onto a specific displacement and then you can correct it for that displacement. So basically it works for any kind of displacement. Let's write the error correcting.
So it's robust against any noise model?
Yeah, in principle,
Really?
it's universal, yeah.
Because even like qubit codes are only resistant against whatever type of the encoding can correct for, right? Like you can correct for like 2 qubit errors in the
Okay, I'm
surface
talking
codes.
about a single,
Okay, so
single
any
mode.
single.
any single mode
Okay.
noise, yeah. I should think about many qubits.
Maybe
Prob-
a super radiant decay or something like that.
I'm sure that in the GKP paper there is a column about
Yeah.
correct. I'm sure. Actually, I know it. Yeah, there is everything in the paper. Okay, I would like to correct to erase the encoded operations, if you don't mind, and also half of the GKP to have more space. And this we leave and we erase it. Okay, so let's draw the error correcting gadget. So the one that comes from the
It's the Christmas tree, I think.
It's the Russians.
I could buy with the yours view clips in the Christmas tree formation. Did you see the Air Force? I didn't see it. The biggest one. Sorry? Well, Christmas spirit, yeah. It shows that we have the beast.
Okay, so the GKP error correcting gadget goes like this. The true one, you have your noisy state. Let's say that we were here with our result of the MBQC. Then you, at the first round, so here I draw that you need 2 GKP. At the first round though, let's see what happens when you use the first one. And I put this wiggle to highlight that these are going to be faulty GKP, in the sense not ideal with infinite squeezing, but they are going to be states with a certain amount of finite squeezing. So then what you do is you entangle it to your state that you want to correct for. Then you measure P in the second mode, and you get an outcome S, and then you perform a displacement of minus S that you got, modulus square root of pi. And here you get something that has, so where the quadrature, one of the 2 quadratures of the input noisy state has been corrected. We are going to precise this further. So this calculation in the original paper by Weck is performed only for Gaussian type of noise. We are going to do a different calculation that is performed by Glancy and Neal. Where basically they model the noise in the GKP as blurred GKP, so as a certain displacements with a certain maybe Gaussian distribution that then correspond to having some finite peak. However, this doesn't model the coherent envelope. So there are some subtleties of this calculation that we are going to do that are not captured by this approach, but it's much simpler, and it really allows to see that there is this replacement of the noise of the state that you want to correct with the noise of the GKP. So this is what we do now. So then, in this case, we model our situation like the following, like as if we had ideal state that comes out, but with a certain noise that is given by displacements, both in the qubit, logical qubit, and this is the first mode, and then in the ideal GKP. So then okay, we are going to do, I mean, as much as we can of the calculation. It's very long, but we do what we can. One thing that I will not calculate, so as it is in the notes, you will see, I'm using first a Heisenberg type representation to calculate what is the expected outcome here when we measure this observable. This we will definitely not having the time to do, so I can tell you the result. And this gives the outcome S is going to be always of the kind n square root of pi plus u1 minus v2. So if you were measuring an ideal GKP state in P, then because of this equation, you know that you would get one of those spikes. So then the n would be random, but if it was about measuring a perfect GKP in P, you would definitely get n square root of pi. That's the only thing that you get in the wave function. You cannot, in the case of infinite squeezing, you don't have anything else. Since here there is some noise distribution and some random displacements, say, and a CZ gate that couples to the noisy displacement of the first mode, then you get some correction that depends on the noise. And then here we displace by minus s modulo square root of pi. So then we get this v2 minus u1. And there is a fault tolerance condition that is that we are able to correct when the modulus of this u1 minus v2 is smaller or equal of square root of pi over 2. Why? Because suppose that your logical encoded qubit, it should be somewhere here, but it has been displaced by some random noise. Then you do a measurement, and if the noise is small enough, then you can, when you correct by displacing back with s modulo square root of pi, you can interpret correctly, and you come back to the original encoded state. If instead is too big, you might basically correct to the one logical state if you had a 0, or to the 0 logical state if you had 1. So you make a logical error. And in the original GKP paper already, this probability of error, depending on how broad the peaks are when the squeezing is finite, is quantified. It gives rise to an error function that is already present in the former GKP paper. But we are not going to say much more details about this. We just want to show that this gadget does a replacement in the noise. Okay, so let's start with the calculation. What we have, what we want to compute, basically the action of the operator, the projector. PS is my homodyne projector in P. When the observable P is measured, getting outcome S. And this is going to act on this psi12, which is the state here. So we are going to compute this state first. So we can write exactly what it is from the circuit. So what we have to start with the perfect encoded state, the perfect looking state, and then we have to apply this displacements, and then the CZ. So then is CZ on minus I U1 P1 minus I V1 Q1 I U2 P2 minus I V2 Q2 on psi L and 0L, where these are the perfect ones. Okay. We also use that to be a bit more formal. So here we are measuring mode 2, and we have the identity on the first mode. So let me write the projector a little bit more formally, like the identity, let's say like this. Identity on mode 1, tensor S on mode 2 in P. So this is the integral in the Q1, 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 tensor S in P in mode 2. Okay. Then if I replace the projector here, we obtain the integral in dq1 of eigenstate q1, q1 times s, and then we have the cz acting on all of this sequence. The cz, by the way, remember that it is e to the I, q1 and q2, where these are operators. And then we have all this sequence. For the moment, I don't copy. I'm trying to do some extra step, or maybe it's just clearer if I copy. Okay. Now, so the Q1 has this for eigenstates. So then this variable becomes replaced by Q1. And then this becomes a translator in the variable of mode 2 of an amount that is Q1. So then this S becomes replaced by S plus Q1. Actually minus Q1. So this we can do. Then let me see if we can do some extra step. Now here we have this, which is for mode 1, it's a translator in Q. So then I can translate this actually. I'm translating by U1 with the sign minus. And then here we have the other mode that we said was S minus Q1. Then here we have e to the minus Q1, Q1, Q2, Q2. I hope it's correct. So this I'm copying, this I'm copying, this I'm copying. This I've acted here and I've translated, and this I've acted and I've translated. So it should be fine. I believe it's correct. Then what else do we have? We have that this is an eigenstate of Q, what we have in the first mode. By the way, sorry for the confusion in notation, but Note that this mode is an eigenstate of Q, and this mode is an eigenstate of P. I'm going to mix a little bit, but it should be clear enough, I believe. So then, when we act, since this is an eigenstate of Q, then this operator just gives a phase. And since this is an eigenstate of P, this operator gives only a phase. So then, summing all two up, we get V1 U1 minus U2S integral in dq1 e to the minus I V1 minus U2 Q1, and then here we have Q1 minus U1 plus, and then S minus Q1 plus V2. So L, 0L. Yeah. So then we have used all of the operators. Okay, and okay, so then what we do now is that we make a use of the fact that the variable S is expressed like this. So we copy S here. So then here we get e to the I. V1 U1 minus U2. I'm just replacing U1 plus N I minus V2 integral in dq1 into the V1 minus U2 Q1 and then Q1 minus U1, and here we have N squared of pi minus Q1 plus U1 on side logical. So yeah, we just replaced this basically, nothing more. And it has affected here and here, phase. And so then we can do a change of variable that Q1 goes to, is equal to Q1 minus U1, and then we drop the prime. So here we get e to the minus U2 n square root of pi minus V2 integral in dq1 1 plus 1 Q1 n square root of pi minus Q1, and this is it. Okay, let me see how much steps I can do and how much steps I should skip. I should skip because it's almost the time. So I will erase that same part actually, the first parts, if you don't mind, because I would like to keep the last equation, and I would like to keep the gadget to show you the replacement at least. Can I erase? You have it in the notes anyway. So I will try to speed up. Maybe I can give you the result and then comment. So an important step that is used here is the fact that when we focus let me just say this, yes, that when we focus on the overlap of n square root of pi minus q1 with the zero logical, so n square root of pi minus q1 with zero logical, this was an eigenstate of p. So then this becomes the sum over L in all the integers, n square root of pi minus q1, L square root of pi, and then this gives a delta. So eventually this becomes a delta q1 minus L square root of pi that you insert in the integral. And this allows you to remove the integral in q1. Okay, so let me jump to the result and then we comment on the result. So after steps, what you get is that your projected state at the output here, let me call it psi out. So this is e to the minus I u2 s minus u1 v2 q1 e to the minus I v1 minus u2 q1 psi l. So the crucial point here to observe is that in the beginning the mode 1 had noise parameters u1 and v1, and the mode 2 had the noise parameters u2 and v2. So after this first round of gadget of error correction with the displacement and so on, yeah, later you have also to do this later step, it is the last displacement. What has happened is that in your p quadrature, you have replaced the v1 with the v2. In practice, the noise parameter, fluctuating parameter, that was affecting your state, u1, has disappeared, and you have replaced it with the noise of the GKP. Now, in the other quadrature, you have that the noise has been added. But then the trick is that you're going to concatenate this twice. So this gadget, so you have your state psi, your zero logical. Then you perform a Fourier transform. So here you correct, this corrects P. Then you do a Fourier transform, so this switches P and Q, and this you do it again. Okay, I don't remember exactly to what this should be attached. And then basically when you switch and you correct again, you correct the Q after having corrected P. So in the second round, you are going to replace the noise in the quadrature Q1 with, so Q1 has become P1, and then this will be, eventually, it will only have the noise U2 that was appearing here. So the bottom line is that this gadget allows one to replace the noise parameter that affect your logical noisy state with noise properties of the GKP only. And the assumption is that this you are going to be able to keep under control. So the assumption of this is that you are able to have fresh GKP states that are not too noisy, that are squeezed enough, so that you can basically keep under control the noise of your logical qubit after that you perform this gadget twice. Do you have questions? Okay. Otherwise, I am afraid that it's already 3. I just, maybe wanted to comment that now it has become a fair field of research, because there are the experiments, people can do the GKP in the lab, they can do big cluster states in the lab, yeah.
So the assumption of this error correction model is essentially that it only affects the noise only affects a single quadrature. It doesn't affect, say, like two-mode squeezing, like you don't have some noise on a two-mode squeezing.
A tool squeezing would be a, yeah, two modes that are like, I don't know how it is treated. In the Nick paper, he had a noise in the CZ gate, and this he can
That's
correct,
too, yeah.
which is probably equivalent, I suspect. So in the paper by the PRL, he shows how to use the GKP to perform fault tolerantly a CZ gate, for instance. So then I imagine that you can correct also when you have noise on both modes. Okay, then we can stop here.